Calculus, one of the most important and diverse systems of study.
What creates this theorem? Where do they come from? Many of these theorems, of these new evolved and derived theorems, comes from a common ancestor, the fundamental theorem of calculus. Tonight, we will be examining the property of this theorem and attempt to understand this free and wild beast. So where do we begin our search? Well, like all mathematical beasts, the fundamental theorem of calculus most likely roam and dominate in the very core, the very forest of mathematics. In other words, the mathematics. So let's begin this trek.
Here we see the fundamental theorem of calculus in its natural habitat. Notice that it is comprised of two distinct parts. Part 1 on top and part 2 on the bottom. This magnificent living theorem was first discovered in the 17th century by Isaac Barrow, a great mathologist. Though some experts say that it was actually first spotted by James Gregory even earlier. However, during his tenure at Cambridge, Isaac Barrow was the first to provide a full general proof that predicts the physique of the organism. Before this time, the two domains of calculus, differentiation and integration, were believed to be non-related, but Isaac Barrow spotted a hybrid caused by the intermingling of the separate domains. However, it wasn't until two other mathologists, Isaac Newton and Gottfried Leibniz, that captured and examined this creature in further detail and were the first to fully confirm this theorem as the offspring of the two domains, and provided a rigorous and systematic way to utilize and identify this theorem. Exactly what did Newton and Leibniz find? We have interviewed an expert in the field to explain.
Good morning, Dr. Einstein.
Good morning.
I know you have been studying the fundamental theory of calculus for many years now.
That's right.
Can you tell us the significance of the FEC?
Sure. So, before the emergence of the fundamental theorem of calculus, what we needed to do in order to evaluate the integral of say a function little g of x between the numbers a and b was to evaluate a Riemann sum, which is basically dividing the area of interest into an infinite number of rectangles and determining the sum of the areas of the rectangles.
Oh, I see. So using Riemann sum, this appears to be a very tedious process.
Yes, it was indeed very tedious.
You're studying a different method to evaluate this integral.
Yes. So the way we go about doing that is, the first thing we do is we characterize the area itself as a function a of x. And we differentiate this function by first principles in order to get this expression, which is basically saying the derivative of the area is the difference between the area function at x plus change in x and x all divided by the change in x. And this is important because from this we can use the mean value theorem to substitute the numerator for this expression.
Oh, I see.
And then from this expression, we realize that there's a change in x in the numerator and in the denominator, which can cancel and give us this new function, little f of x.
Oh, so this appears to be very obvious now. The area under the graph for the function little f of x, there's just inverse operations.
Yes, integration and differentiation are inverse operations.
So now that you have defined integration and differentiation as inverse operations, how would you go about solving this problem?
Well, first, we use that concept and come up with this expression, which says that the area function a of x is equal to the integration of some function little f between a and x.
I see. So we were evaluating the area between a and b. Why is it that there's x here instead of
Well, the idea is, we're going to set some x around maybe this area, and we're going to make the x in this equation approach b, giving us the area.
So you're manipulating the algebra here.
Yes, that's exactly right.
Oh,
Okay, so the next step we do is we find out what evaluate this function at a. So that's basically a to a of f little f of t, which gives us 0 because it's in the integration underneath the point, right? And so,
I see that.
and then we evaluate this function at b, which would give us this equation, which is what we're trying to solve for. And so, before we move on, first we'll generalize this, the equations that we're working with. So the area function a of x is equal to the antiderivative of little f of x plus c. And what c is a constant, because, for instance, if our little f of x was the function x, then the antiderivative would be x squared all over 2 plus c, because information is lost during the integration.
Oh, I see. So if this t was on, say, 1 or 2 or 3, then the derivative of this function is still going to give us the same little f of x, which equals x.
Precisely. So, with that in mind, we substitute the values of x as little a, and because we know the area function value at little a gives us 0, we can find c, the constant, to be equal to the negative f of capital F of a, which is the antiderivative of f of a. So then we use the same equation except for our area at b, with the knowledge that c is equal to negative f of a, and that gives us this expression, which states that this is equal to the difference of the antiderivative value at b and a. So that's our final expression.
And this is the fundamental theorem of calculus.
Yes.
Thank you, Doctor. Thank you very much for your time.
These are gentle creatures, yet they are often very evasive against those inexperienced facing with the theorem. So let's try to approach it very quickly. Where did it go? Gosh, the theorem disappeared.
Oh, it seems like my friendly neighborhood Spider-Man has captured this fundamental theorem of calculus. So, what makes this creature so powerful is that, and dangerous is that it is very, very versatile in manipulating equations and deriving new theorems. It has developed into a keystone species in the global math system.